Yeah, this is really exciting and really inspiring. I have to ask then, what timeline do you think, like first working out there nuclear fusion power plant? When
hmm
do you think?
Yeah. So what we've been able to do is rapidly build every few years, bring a new fusion system online. Um, in 2023, we signed a deal with Microsoft to build a power plant for Microsoft for one of their data centers. And this is a power plant that is plugged into the grid, generating electricity from fusion. And with a very, very tough, ambitious timeline of 2028 for the first electrons from that power plant.
And that power plant will be powering a data center.
That power plant will be powering the grid that the data center is plugged into. And we can get into the details of how the power grid works and such. But yes,
Mhm.
so Microsoft will be buying the power from that power plant.
Props to Microsoft for like creating a hard deadline. I love it.
They are, and it is daily that we think about that deadline. We had been working with them on and off through all of those machines, through Grande, Venti, Trenta. So they had seen us hit milestones, show that we can do fusion, scale up by orders of magnitude, and then access these advanced fusion fuels. So they had seen all of those things, and seen the manufacturing we've built. We're already right now building the manufacturing to support that power plant. We're doing that today. Um, we started 2 years ago on doing the work around siting, around the interconnects. How do you plug fusion in? What does it look like? How do you site it? What are the environmental consequences? Who's going to regulate it? All of those things. So we spent a lot of time already, and we're on our way. And it's going to be hard. Like, no joke about it. This is tough, and it's something that I think about every day.
I'm sure you've had a bunch of people probably still tell you that this is a pipe dream, like this is impossible. Are there days that you and the team think that this is indeed impossible? And then you wake up the next day and you're like, all right, we're gonna do it anyway.
I mean, that's the thought process. That's the mentality. We're going to do it anyway. Let's go do it. The world needs it. There's no physics reason this can't be done. Now it's a question of how fast can you build it, and can you engineer it to be as efficient as it needs to be. And those are engineering and manufacturing are ridiculously hard challenges. So do not short sell that. But that's the goal, and that's what we get up every day thinking about. This is something I was actually just thinking about and talking with some of my team in the last few days. We certainly have people that say like, no, this can never be done. And we had that before. We had that at the very beginning of, I want to go merge these plasmas together, and folks said, nope, that can never happen. And we went off and did it. And you can't compress an FRC because it's unstable. In fact, I actually still hear that FRCs are unstable. And I say, yes, I know. Now let me introduce you to S star over E and 20 years of studies on what we know about that and how we can combat that. And so we've been able to show through lots of skepticism that we can still build and iterate. And there are things I don't know. I'm like, let's just be totally honest. As we're going to go build these things, we're going to discover new hard problems. If we're not doing our job, if we're not discovering new hard problems, we probably didn't push hard enough. We probably didn't push fast enough. And I think that's really critical. That we build the team, and we do the hiring to make sure that like everybody is doing that problem. Now that doesn't mean it's not a hard challenge, and to keep folks motivated. Helion now is over 500 people, but when we built Trenta, we're 50 people.
Okay.
So now there's over 300 humans working at Helion that didn't see us build a system from a computer model, bring it online, and do fusion with it. But even already for Polaris, there are lots of humans that started for our 7th generation system. When we were running Trenta, doing fusion, they were able to see the measurements, know we were doing fusion, but yet this next machine was just a simulation. And so seeing that get built, seeing that, like, it's just awe-inspiring for folks. And I'll tell you, the first time that it comes online and flashes pink and you see that fusion glow, it's awe-inspiring. It's awe-inspiring.
I love that. The fusion glow. Yeah. Yeah.
Everybody changes their Windows desktop backgrounds to now the fusion background, the plasma glow.
So how can you actually see it?
It's a couple of things. So one, to get access to it, we have Windows. We have small windows all the way around that we look into it with cameras, spectroscopy, lasers, other kinds of scientific diagnostics that we use to measure. So you see the light emission through that, but also it's very bright.
Yeah.
And so the actual vacuum vessels themselves that we use are ceramic. They're some versions of silicon and oxygen, typically quartz, but there's also some other sintered materials. And it's so bright that they can shine through those materials. And so what you see is you see the light of not fusion. When fusion's happening, thermonuclear fusion is so hot that the light is in the X-ray spectrum, and the human eye can't see that. But as you're that ice cold 1 million degree plasma, when you're just getting started, it's emitting photons in a range and light in a range that humans can see. And so you see that bright purple fuchsia color.
And this would be, if you're doing actual cameras, this would be like extremely high speed cameras, that kind of thing.
We have high speed ones and low speed ones. The traditional SLR cameras, which the ones that represent the right color, all they catch is the light, the integrated light, the flash. They don't know, they can't see the plasma forming, accelerating, compressing. They can't see any of those things. They just see all of it integrated into one bright flash. But the high speed cameras, they can see that. And so the high speed cameras we can use to actually measure that. In fact, we put special filters on them to measure different wavelengths of light. So we can tell, is it the hydrogen? Is it the heliums? Is it the helium-3? Who is emitting the light? When are they emitting? What particles are emitting the light and when? And so by using those advanced diagnostics, we can now take movies of that. Though it's not as great as just seeing that flash.
Yeah, I mean, it's beautiful, right? That human beings are able to create something like that. It's truly beautiful. Just out of curiosity, are there some interesting intricacies connecting the nuclear fusion power plant to the power grid? Like, is there some like constraints to the old schoolness of the power grid, let's say in the United States? Like, how do you get that Microsoft thing you mentioned? How do you get from the nuclear fusion power plant to a computer with some GPUs?
Mm-hmm.
How do we make that connection? Or is that a trivial thing?
None of this is trivial. But there are, I think, simple ways, and there's some really interesting engineering ways to do this. So just from the fundamental basics, as we're doing fusion, we push back on the magnetic field. We recharge these capacitors that start where the electricity started from. And that electricity then sits on a capacitor at high voltage, DC voltage that's steady. At that point, it's reasonably easy to make 60 hertz power, make traditional AC power. It's the same way as you can take electricity in a battery and use an inverter and just invert that to AC power. And large-scale grid inverters, we know how to do pretty well. One of the sort of like unique things about a pulsed version of this, because it's pulsed and a repetition rate between 1 and 10 times a second, we can adjust the power output. And so as the grid needs more power, we can actually dial it up and down. And we've been able to demonstrate that with our fusion systems. The smaller ones, the smaller plasma systems, we've gone from 0, from off, to all the way up to 100 times a second, and shown we can do 100 hertz operation. In fact, that system we ran for over 1 billion operations and just ran it steady all day long.
So each individual pulse is independent in some sense.
Each individual pulse is different, where you put in your fuel, you do fusion, you exhaust it through those pumps from eBay, and then power output and electricity output.
Wow.
But there's probably some more clever ways to do this. And when we founded Helion, the goal was to build low-cost baseload electricity. And what we started to see, working with Microsoft, working with others now, that data centers are going to be one of the biggest power needs in the future. And we know that's coming up. And what's really unique is that power in this form, this direct recovery, not the steam turbine part, but direct electricity, is already DC, which is steady, which is what computers really want anyway. And so are there really unique ways to take DC power sitting on this capacitor, and rather than going AC to the grid and having all these transmission losses, just going direct DC to the data center? Can you plug right in? And so that's some of the things that my team is looking at now is, can you do that direct DC conversion at super high efficiencies and run those GPUs directly? That would be really powerful. We could figure out how to do it. But But those are some of the things that I think there might be some unique ways that fusion and data centers can really couple together. There's a whole cooling part to it too. Most of my cooling is cooling semiconductors and cooling power switching, just like a data center. So there's a lot of interesting engineering ways that we can bring those two together.
So a deeper integration between the power plant and the thing that it's powering. And it does seem like the future, quite possibly, a lot of the energy that's needed will be for compute, for AI-related applications. So if you just look out into the future, 10, 20, 50 years from now, do you see nuclear fusion as a thing that powers these gigantic data centers of millions of GPUs? Just basically the surface of the Earth covered in compute and nuclear fusion power plants. Maybe that's 100 years out.
So when I talk to AI experts, they talk pretty routinely about the power needs for AI. And in fact, in the same way in manufacturing that the cost of any one thing asymptotes to the raw material, for AI, the cost of computation asymptotes to the power, to the cost of the electricity. And even more, that electricity is concentrated. It's in that AI data center, that brain where all the power is. And you really want a lot of high energy density. You want power generation right there on site. So it seems like, just take those two facts, a really nice match for between fusion, which is baseload, high energy density, can be sited most places, and a data center, which is going to be high energy requirements in a local location and large amounts of it. There's been predictions recently from energy institutes that suggest we will have growth that, rather than a 2% growth per year in electricity, maybe a 4 or 6% growth in electricity due to data center use. I think that is probably wildly underestimating where we're moving. And so,
oh man.
And so the idea that AI can grow human cognition and our ability to solve problems, we can't let it be limited by power. And so I'm going to push as hard as I can so that's not the limit.
Do you ever think about like 2050 or something like that? Just I know you're focused on a few years out, just getting a fusion power plant working, but do you ever think about like even longer term future? You see, by what year do you think there'll be over 1,000 nuclear fusion power plants?
So I tell the team that if we demonstrate fusion one time and that's it, then we failed. But that's not enough. That's not the universe is powered by fusion. Humans need to be harnessing this and can harness this for our society, for the good of society, for the good of technology. And so that's something that we push towards. And in fact, it's baked into how we design these machines. Coils are mass produced, capacitors are mass produced, and we make them all across the board. Is thinking about not what the next system's going to be, but making sure we're building the manufacturing and the infrastructure to build all of those systems. So we had a call from the White House a number of years ago for the bold decadal study in fusion of how do we get fusion, and it was Helion and a variety of other companies from the fusion industry. And it's pretty awesome to be able to say there's a fusion industry now. That it's not nice. Just a one-off thing, or there's a fusion experiment, or somebody has a prototype, but like there's an industry.
Yeah.
That Helion has competitors.
Yeah.
That's great.
I've never heard anyone so excited to have competitors, but yes, that's like a serious thing. That's a real possibility. Yeah.
And the goal was, how do we not just demonstrate fusion in the next decade, but meaningfully deploy it and start to answer. We have 4,000 gigawatts of installed fossil fuel capacity. How do we start replacing that with fusion in a meaningful way? And how do we get to not just making a generator every few years, but we want a gigafactory of these fusion generators rolling off the line, one a month, one a week, one a day. And that's the kind of plans that I task my supply chain team with like how do you do this? How do we actually go build this? How do we go build a gigafactory so we can have 50 megawatt generators coming off the line, being deployed on a truck, and then driving off the factory every day? And it's a tough challenge. I see what others have been able to do in rockets, in electric vehicles, turning around huge factories. We know this can be done, and so for fusion, the call is there, and the market is there too. If you can get electricity generators cheap enough, then it's worth doing.
Yeah, I mean, all of this is really exciting and inspiring what you're doing, and obviously the world needs it. And the more cheap energy we have of this kind that we describe, clean, and it's not constrained to geographical locations and so on. First of all, that alleviates a lot of the tension that in geopolitics, but second of all, it enables a lot of the technological breakthroughs on the AI side,
Mm-hmm.
on all the different things that we use compute for. It's really, really exciting. So yeah, I hope there's like millions of them in the coming decades.
And so if we can get to that, if we can get to making a generator a day, you're
Yeah.
not now talking about hundreds a year, and you're deploying them.
Yeah.
And deploying them is also hard at this scale. How do you go and deploy power plants and deploy generators at this scale and do it quickly? Interestingly, data centers are a little bit of a nicer challenge in that way because we wouldn't build one 50 megawatt system and have to go build a site for it. We'll build a site and put 100 of them on that site and have large amounts of power for that large data center. And so that in some ways is actually in the chicken and egg problem of how do you go deploy hundreds or thousands of fusion generators. Data centers are an interesting application where very immediately you need a lot of power in a very small area, and you can go do that. Now, what does that mean? That means I'm going to need more than 2 conveyor belts. That's for sure.
Yeah. Yeah. Well, you have to, I mean, manufacturing is really hard. But like you said, the fascinating thing is it's hard, but as you're doing it, you figure out all the other things, the science and the physics and the everything. Everything, the innovation is accelerated when you have to manufacture at scale. It's actually fascinating to watch. You see